Welcome back to another explainer. Today we're diving headfirst into a highly structured, pretty energetic journey through the master science of matter itself. We're going to explore exactly how the entire universe is built, broken down, and fundamentally transformed. Let's get into it.
So, when I say the word chemistry, what's the first thing that pops into your head? Probably a scientist in a crisp white lab coat holding up a bubbling test tube, right? Well, I want to challenge you to think a little bigger today. Much bigger, actually. Because chemistry isn't just something that happens on a lab bench. It's essentially the fundamental operating system of our entire universe.
Okay, let's dive into this. To really grasp the sheer scale of this universal operating system, we need to go straight to our foundational text. It starts right at the top with a super clear, uncompromising definition of exactly what we're dealing with today.
Right here in the text, chemistry is defined as the science which deals with the properties, composition, and structure of matter. It studies both the physical and chemical changes matter goes through and, crucially, the laws or principles governing those changes. But here's the thing, matter is literally everything. It's way too vast for anyone to study all at once. That's exactly why scientists need distinct branches. By carving this massive subject up into specific areas, researchers can focus deeply, and that is how we achieve real breakthroughs. Which brings us perfectly to how we've organized our exploration today.
To keep things organized and prevent any cognitive overload, here is our roadmap. We just covered defining the master science. Next up is the fundamental core, followed by the chemistry of life, Earth, space, and beyond, and finally, designing medicines for humanity.
Moving right along to Section 2, the fundamental core, physics, analysis, and the nucleus.
Now, what's really interesting about this grouping is how it breaks down the raw, atomic nature, and rigorous analysis of matter across three foundational branches. First, you've got physical chemistry. This investigates how substances behave at the atomic or molecular level, and it's used to optimize reaction rates on a massive industrial scale. Next, analytical chemistry is all about breaking things down, separating, identifying, and finding concentrations using modern instruments. And finally, nuclear chemistry goes straight into the heart of the atom itself, dealing with radioactivity and the actual transformations happening right inside the nucleus.
All right, Section 3, the chemistry of life, from carbon to complex organisms.
So, we've covered the fundamental atoms, but how do they actually build living things? Well, this brilliantly illustrates a crucial dividing line in the chemical world. On one side, we have organic chemistry. This is the realm of carbon compounds and hydrocarbons, which are absolutely essential for all forms of life. On the flip side is inorganic chemistry, focusing on elements and compounds with little to no carbon. But hey, don't let the lack of carbon fool you. Inorganic compounds are totally vital to our world, driving things like fertilizers, medicines, and catalysts.
As we move down the list from inorganic materials into the life sciences, you can see the chemical definitions get incredibly densely packed. Precision here is key to understanding how life actively functions. Building right on top of those organic carbon compounds, we hit biochemistry. This is the branch where we actively understand life through chemical processes. It's the study of the substances and the vital processes occurring right now inside living organisms. Basically, it takes the what of organic chemistry and digs deep into the how of a living, breathing entity.
Specifically, biochemistry gives us the essential blueprint for the molecules keeping us alive: proteins, carbohydrates, lipids, and nucleic acids. Every single time you eat, breathe, or even move, you are relying entirely on the biochemical reactions of these exact molecules.
And closely related to those building blocks is polymer chemistry, which focuses on the properties, structure, and synthesis of polymers and macromolecules. Think of polymers as these long chains of repeating molecules. While we typically think of manufactured plastics when we hear the word polymer, it actually connects directly back to life itself. Lots of materials present in living organisms, including the proteins and nucleic acids we just talked about, as well as cellulose in plants, are naturally occurring polymers.
Okay, Section 4, Earth, Space, and Beyond, Our Planet and the Universe.
Now that we've mastered microscopic chains of life, it's time to drastically shift our perspective to the macro scale. First up is environmental chemistry. This branch tracks the chemical and biochemical phenomena happening all over our planet, across the air, the soil, and our water environments. So the crucial point is this. Without it, it would be entirely impossible to study the effects we humans have on the environment or figure out the solutions for different types of pollution.
Right beneath the air and water lies the solid ground, and that is the domain of geochemistry.
This is the study of the chemical composition of the Earth itself, its sources, and its minerals. And you know, it has incredible practical applications for our modern world. Geochemistry is actively used in mineral exploration, mapping, and it even plays a vital role in environmental monitoring, forestry, and medical research by helping us understand the terrestrial elements we interact with every single day.
Let's move on and see how this builds, because as we leave the Earth's crust in the rearview mirror, we transition into the absolute final frontier, space itself.
This brings us to astrochemistry. The scale here is frankly staggering. We're talking about the study of molecules and ions reoccurring not just in our immediate solar system, but throughout deep space and interstellar space. This discipline tracks the abundance and reactions of molecules and ions in the universe, specifically focusing on how they interact with radiation across the vast, freezing expanse of the cosmos. It is literally chemistry on a universal scale.
And finally, Section 5, Designing Medicines for Humanity, Chemistry's Culmination.
So let's bring our focus all the way back down from the stars to something deeply personal here on Earth. There is a beautiful, clear mandate for this final branch. The chemist tries to design and synthesize a medicine or drugs which is beneficial for mankind. Medicinal chemistry represents the ultimate practical culmination of all the knowledge we've discussed today. It's focused entirely on directly helping people and improving human health.
But you know, just designing a drug is really only the first part of the battle. Medicinal chemistry includes tracking a drug's entire journey through the human body in a highly precise 4-step process. First up is discovery, finding that active compound. Second is delivery, actually getting it to the right place. Third is absorption, ensuring the body can take it in. And fourth is metabolism, understanding exactly how the body utilizes it. This rigorous process is what ensures life-saving drugs work effectively and safely once they enter our complex biological systems.
We have covered some incredible ground today, from the microscopic reactions happening inside the nucleus of an atom, all the way out to the interaction of ions and radiation in the cold vacuum of interstellar space. The sheer scope of what this master science covers is just breathtaking. So, I'll leave you with this final thought. Considering the massive challenges and mysteries we still face as a species, which of these branches of chemistry do you think will drive humanity's next major scientific breakthrough? Thank you for joining me on this explainer, and keep exploring.